True or false? Block matrix A is automatically symmetric. Yeah, no, that's A is a false statement. You know why? Right, because this has to be symmetric if this equal to its transpose, and its transpose will be 0 A transpose and A transpose 0, which means A has to equal A transpose. So A has to be symmetric for it to be symmetric. But it doesn't say that. Right? So it's not necessarily true, no. So A is false. Okay. How about B? If A and B are symmetric, then their product is symmetric. Well, let's find out. If A is symmetric, then A equal A transpose, and if B is symmetric, then B is equal to B transpose. By definition, that's what a symmetric matrix mean. Then their product is symmetric. Well, let's see what AB is. AB is A transpose B transpose, because they're the same, no? And so this would be BA. First of all, the product would be symmetric if, let me erase this last step here, write it slightly different. The product is symmetric if this equals to its transpose. Let's see what AB transpose is. So are these equal? That's the question. AB transpose. So remember, when we take the transpose of a product, we do distribute the transpose of each one. However, we reverse the order of multiplication. So this will be B transpose A transpose, right? This is equal B transpose A transpose, but B transpose is the same thing as B, and A transpose is the same thing as A. So then the question, but that's not necessarily true, because AB does not necessarily have to equal to BA, and therefore AB does not necessarily equal its AB transpose. So AB is not symmetric matrix. So AB is not symmetric. So the second statement is also false. Okay, part C. If A is not symmetric, then A inverse is not symmetric. Well, let's take a look for part C. So then this becomes if A is not symmetric, then A inverse is not symmetric. Okay, so A inverse would be symmetric when its transpose equal to the original. But A inverse transpose is the same thing as A transpose inverse, right? But in general, A transpose, well, in this case, because it's saying A is not symmetric, A is not symmetric, meaning A does not equal its transpose. And so A inverse transpose equals 1 second. Yeah, so for the inverse to be, if A is not symmetric, A inverse is not symmetric. If A inverse is not symmetric, then we are trying to prove that A inverse. 1 second here. Let me rewrite this a little bit different. So if A is not symmetric, then A inverse is not symmetric. A inverse is not symmetric. That means we're trying to say that A inverse does not equal in general. So there's a question mark over this. It's A inverse transpose. But we know for sure that A does not equal A transpose because A is not symmetric. Okay, well, let me inverse both sides here on this second equation. So then A inverse does not equal A transpose inverse. But A transpose inverse is the same thing as A inverse transpose, and hence I can replace this. I could replace this here and come to the conclusion that A inverse does not equal A inverse transpose, and if they're not equal, therefore A inverse is not symmetric. So the third statement is a true statement. Okay, the last one, it says if A, B, and C are symmetric, then the transpose of A, B, C is CBA. Okay, let's test that. So if A is symmetric, then A has to equal A transpose, and if B is symmetric, B has to equal B transpose, and if same thing for C. So they all have to be the same as their transpose. This is the definition of a symmetric matrix. So now, considering these, if I take ABC and I transpose that, because I'm trying to see whether the transpose is actually CBA, so let me transpose this. So we said that when we transpose, we distribute the transpose, except we reverse the order of multiplication. So this becomes C transpose, B transpose, A transpose. Okay, but we just said that C transpose is C, so this is C, and B transpose is B, and A transpose is A. So indeed we get exactly what the question is saying. We get the transpose of ABC is CBA. So yes, it checks, and this statement would be true. That does it.